Hello, everyone, and thank you for joining us today for this e-showcase, design, startup, and operation of Utah's first deammonification system. I want to take a little time to thank our sponsor, Veolia. Thank you so much for sponsoring today's e-showcase. And so I have the pleasure of introducing today's presenters. Philip Heck, General Manager, Central Valley; Dustin Glore, Process Coordinator; Rodrigo Lara, Regional Sales Manager. And without further ado, I will hand the presentation to our presenters.
Thank you, Regina, and thank you everyone for joining today's webinar. Today's agenda, we're going to go over the brief overview of the deammonification system offered by Veolia. Then Central Valley will go into their slides going over the timeline of deciding the side stream process of treatment that was chosen, along with nutrient removal process as seen at the facility. They will then go into the process and financial benefits, along with the solution selection and startup of the anammox system. And finally, we'll end with question and answer session. So I'll quickly start a brief overview of the anammox deammonification technology and give an update on some of the progress made for side stream treatment. To start the presentation, I would like to show a typical wastewater treatment facility, starting with the above section showing the mainstream part of the facility from headworks to discharge. Below the mainstream plant is the side stream process, now including thickeners, anaerobic digesters, and dewatering. Where anammox comes into the side stream process is after the dewatering stage. Anammox is able to treat different liquid streams, either from centrate or filtrate. Anammox helps remove ammonia and total nitrogen directly from centrate or filtrate, or combination of the two, before it is sent back to the head of the plant. Benefits for deammonification and overall plant improvement will be discussed later in the webinar by Phil and Dustin. Anammox operates in two separate process modes. As you will see here on the left side, we have the MBBR process, and to the right or in the middle, you have the IFAS process. To start with, the MBBR is for regular centrate or filtrate treatment. The MBBR application is the most simple process of the two because it is a single pass treatment system and is great for retrofitting existing tankage, including shallow tanks. Our second mode, IFAS, has the benefit of having both suspended growth and biofilm due to the use of return activated sludge by use with a clarifier. The IFAS option would be mainly for THP or food waste co-digestion systems. The anammox media and in-basin equipment, as shown in the right slides or photos, is an equipment shared Veolia has been using for decades in the mainstream process for traditional MBR or IFAS processes. We've now incorporated that same media and internal tank equipment to now treat anammox bacteria. The equipment that we've used for mainstream MBBR or IFAS has been in operation around the world for over 20 years and has been highly successful. So we have taken a proven technology and incorporated it into a new process opportunity. Biofilm technology proven to be simple, stable, and robust. Some of the benefits that you would expect to see and will be covered by Phil and Dustin are its operator-friendly technology, resilient, it works with flexible dewatering schedules, minimal operation and maintenance requirements. Biofilm technology, it significantly lowers risk of anammox washout. It's very tolerant to high TSS, polymer, DO, pH, and etc. It also has greater protection from shocks and toxicity. As mentioned before, it is able to reuse existing tanks with a wide water depth and geometry configuration capacity. And it also has capacity increased by adding more media over time as the plant requires more process treatment. Running out the anammox overview, our existing plants are all operating as designed and are fully open to visitors. We have also had a number of facilities recently add in more media fill for increased performance. Anammox has been pre-selected on a number of upcoming projects, so please keep a lookout for announcement on Veolia's social media. We are continuing to pilot anammox across the U.S. and have recently added in more pilot units, so we are able to continue to offer piloting at facilities around the U.S. Simultaneously. And with that, I'll turn it over to Phil Heck with Central Valley.
Well, thank you all for joining this webcast. I'd like to talk a little bit about Central Valley Water Reclamation Facility and our experience with anammox. First, just to orient everyone, Central Valley is a regional wastewater treatment facility, and we're located at this Gold Star just south of Salt Lake City, Utah, and we serve the central part of the Salt Lake Valley. On the east side is the Wasatch Mountains. That's where the ski areas are that most people are familiar with. And then the west side of the valley is the Ochre Mountains. So a fairly large area, about 615,000 people. And we're currently undergoing some plant upgrades and expansion that'll take our capacity to 84 MGD. Okay, next slide. Back about 10 years ago, the state of Utah Water Quality Board implemented a new rule that was called the Technically Based Phosphorus Effluent Limits Rule. That required all treatment plants in Utah to reduce their phosphorus in the effluent to less than 1 milligrams per liter. We were a trickle and filter solids contact plant at that point. We currently operate under that mode, and we could not remove phosphorus or nitrogen. So we immediately started investigations on how we were going to meet this new rule. We hired an engineering firm, started a process selection process, and once we figured out what we were going to do, we did pilot testing back in 16 and 17. When we confirmed our designs and selection would work, we started design. And then in 2020, we actually started construction of our main biological nutrient removal process. And this is a process that will remove both phosphorus and total nitrogen. As part of this selection process, we investigated side stream processes for both phosphorus and nitrogen removal from our belt press filtrate. We started the design of these two systems in 2020, and just last year in 2023, we finished construction of both the side stream nitrogen and the side stream phosphorus processes and put those into operation. We are still working on construction of our main biological nutrient process, and that will go into service next year. Next slide, please. So an overview of our plant layout. We have sort of in the middle there, BNR anaerobic basins, and then BNR anoxic and aeration basins. Those are new processes. We have a BNR blower building, and that's all part of our mainstream biological treatment process. And we have a side stream phosphorus removal process that precipitates struvite from our biosolids, our digested biosolids. We have a primary sludge fermentation and thickening process to generate VFAs for our anaerobic basins and for denitrification. We have a dewatering building. We currently have belt presses, but we're also adding some centrifuges in an ongoing process right now. And then finally, we have our side stream nitrogen removal process. And this is treating the effluent from our dewatering process and the filtrate before we return that flow to the back into the primary effluent. Next slide, please. So on a process flow diagram, the upper area is all the facilities related to our new biological nutrient removal process on the mainstream and some solids. And then the two boxes down below are our side stream phosphorus. We've selected Airprex, and then our side stream nitrogen, and that's the anammox process that we'll get into. I'd also like to just note over on the left side, we are adding a facility that we will be starting construction in the next couple of years for high strength liquid waste. That's food waste from some industrial sources. And so we will be bringing that in and co-digesting it. And this is going to greatly increase our nitrogen load in the future. Okay, next slide, please. So in a typical BNR process, I guess the question is, why consider the side stream nitrogen removal? Well, if you look at down the lower part of the diagram, the filtrate returning back to the plant contains a fairly high level of TKN, mainly in the form of ammonia. And this typically is about 15 to 20% of the total nitrogen load on the influent. And so this ammonia that's being returned must then be nitrified and denitrified to successfully operate a BNR system. And this consumes a lot of oxygen and carbon. And so we considered this in the design of our system, and I'll take you through some of the considerations and how it affected our main BNR process. Next slide, please. So this table, I'm showing some of our modeling parameters when we were designing the overall biological treatment process here, incorporating side stream nitrogen and side stream phosphorus. So the baseline BNR column, this is the column of our design without side stream treatment processes. And then the next column over, BNR with side stream treatment. This incorporates both nitrogen and phosphorus removal. And so as you can see, there's a lot of benefits to the side stream processes. We were able to reduce our basin volume of our aeration basins and anoxic tanks by about 16%, or 4 million gallons. Our fermentate needed for phosphorus reliefs and denitrification decreased by about 66%. Internal mixed liquor pumping decreased by about 54%. Our aeration demand is decreased by about 30%. WAS production about 24%, and our total power required by about 28% by incorporating both of these types of side stream processes. I'd say a lot of the benefit here is with the nitrogen removal process, especially with power and fermentate. Next slide, please. We also looked at the financial benefits of both side stream nitrogen and phosphorus removal to the BNR process. And this is the main benefits for side stream nitrogen removal. So our WAS production and then the treatment and disposal of that WAS, the cost savings was about $850,000 per year, incorporating side stream nitrogen. Then on our aeration and pumping power, that's about $630,000 per year. So substantial operational cost difference. On capital cost, there's not a lot of difference between BNR without side stream nitrogen and to BNR with it. There's a small savings of about $4.7 million. But overall, if you look at a net present value over 25 years, doing the side stream nitrogen made sense. And the net PV is about $24 million. So that's a substantial savings to us. Next slide, please. So in looking for vendors for side stream nitrogen, we went about a pre-selection process and then selected a vendor and then designed around that particular vendor's offering. And we developed a committee with our own staff and with our engineers staff and put together the selection process based on experience, design and performance of the system, the maintenance requirements, and then life cycle cost. We asked 3 different vendors to submit proposals, and then we evaluated and scored those. The scoring included the first 3 items. The life cycle cost was hidden from all the committee until the scores on the other 3 were submitted. Then we did the life cycle costs so that we could have as unbiased a process as possible. And that's how we ended up selecting Veolia and the anammox process. Okay, next slide, please. So these are the 3 types, the 3 different processes. We looked at the Deammon process, the anammox, and the anammopac process, and some of the different configurations and ways that they operate. We liked the anammox process. It was a continuous process. We liked the biofilm component of it, and that would minimize the risk of washout. And it also kind of decouples the biofilm and the bacteria associated with the treatment process from all the other solids. So you can have an upset in your dewatering process and have high solids in your filtrate, and those can wash through and they really don't have an effect on the system. So those were some of the considerations that we scored high in our evaluation. Some of the others were that we liked the fact that the process could be expanded readily by just adding fill volume of media to the reactor tanks. So next slide, please. So in terms of our process design, we're designed for about 500,000 gallons per day of filtrate flow. We have several different sequences here that the vendors had to meet. We're going to have a startup period, which we're in right now. We're treating about 1,200 pounds of ammonia per day. Once we get our second reactor online, that'll jump up to about 2,100 pounds. And then once we get our food waste co-digestion online, that is expected to go to about 7,000 pounds per day of ammonia. Our performance requirements for the vendors were to achieve greater than 75% ammonia removal and 70% tin removal. And Dustin will talk about the results today. Next slide, please. Oh, go back one slide. Our system consists of 2 reactor tanks and a building that houses electrical gear and blowers and foam removal or foam anti-foam systems and so forth. Okay, next slide. So this is the process flow diagram is a little bit light, but our system is set up we had a couple of old anaerobic digesters, and we used those as filtrate storage tanks. And in that storage process, we're putting the filtrate in those continuously. Depending on our dewatering rates, the flows vary. We try to feed the anammox process a consistent flow, so the levels in those tanks could vary throughout the day and equalize. We also use those tanks as clarifiers, so they capture any solids that are carried over from our dewatering process, and we're removing that to try to lessen the solids load on the anammox process. And then we have the two anammox reactors and the blowers that supply air to those. We initially built 2 reactors. We have space for 1, and our reactors are 55 feet in diameter with a 21-foot liquid depth and about 380,000 gallons each. The fill volume of media is about 15,000 cubic feet, and so we can add more media to each of these tanks as we need to in the future. We have 3 blowers, so N+1, and they're 60 horsepower each. And for comparison, we were able to downsize our main B&R blowers from 1,500 horsepower to 1,250 horsepower each. So this process was, and that's where a lot of the energy savings is just being able to downsize the blowers associated with your main treatment process and use the air much more efficiently. Next slide, please. So I'll turn it over to Dustin, and he'll talk about our experience with process startup.
Thank you, Phil. I'm the process coordinator here, and I have overseen the startup and operation of the anammox process. It's almost a year now that we officially started up. The first stage, I believe, began in June with the unseeded media going into reactor 1, and we had a primary effluent, and that was about a 2 or 2.5 month wetting process. So the media, plastic media, has a hydrophobic nature, so Veolia does a wetting period to get rid of that, and also it grows a bit of a heterotrophic film on the media. So when we do introduce the anammox and the seeded media, we'll see it attach faster. So yeah, we filled just 1 reactor. We're a little limited on electrical components. So even though we're designed, we have 2 reactors, we've only had 1 in operation this time. The second should come in operation in late September. So we're already in the wetting period for the unseeded media for reactor 2. And yeah, we filled about 5% of our seed media. It came from Durham, North Carolina. And when we added that, we started to add filtrate. So the filtrate replaces the primary effluent sitting in the reactor, and we start monitoring the ammonia levels, nitrite and nitrate, and Veolia was on site to guide us through that and teach us about how to make the right process decisions. So we went from intermittent aeration and intermittent filtrate feed to the reactor, and slowly, it took about a month only, and we were at continuous aeration and fully loading, at least to design load, our reactor number 1. And we've been doing the biofilm growth monitoring. This is a process laid out by Veolia in their tech manual, and our lab's been good about doing this once a week for the first year. And what we wanted to see was how fast it took or how long it took to get our biofilm on our originally unseeded media up to the level of what our seeded media came in at. And so, yeah, at about, so we see here, the seeded media came in with quite a bit of biofilm, and it grew over a 4-month period there, or 6 months in total. You can see the change in growth, and the unseeded media grew at a steady rate too. Next slide, Rodrigo. And yeah, this is the graph showing the biomass weight. So we'll discuss some operational challenges in a later slide, but here you see a big drop in this recent, that was mid-May. We needed to actually spray some of the biomass from the media. We had a floating issue. Still not sure exactly what caused it, but it just highlights the resiliency of this media and the anammox process, that anammox process that Veolia has, that we never went too far below design removal rates, even as we lost over half of our biomass during that period. And it's bouncing back really nicely. So next slide. Yeah, and this is our ammonia loading over the past year, or this the past year that the anammox process has been on, and we're pulling further back just to show our effluent ammonia loading has dropped almost 10%, really from the moment the anammox process reached the design loading. And again, this is just one reactor. So the design loading is about 1,100 pounds at the moment. And it's been, yeah, easy to see the immediate effects of less ammonia at the head of the plant. We've struggled with ammonia removal over the past year due to we have trickling filters, and followed by a solids contact basin. So we had to go from 4 trickling filters down to 3 to allow for construction to continue on the new BNR project. And when that happened, it actually removed our best ammonia removal trickling filter and left us with 3 that struggle. So the anammox process, being able to take on this amount of load and so quickly just before the winter when we really struggle was a blessing. So at the final effluent also, that's the blue line, we've also seen a steady decline in ammonia there. I think we've actually never seen the ammonia at our effluent so low, even in our composite samples, where we've been really low. And we've changed some process operations at the solids contact basin to help with that, but it's definitely been this 10% drop coming into the head of the plant that's helped out. Next slide. So the operational challenges that we faced, a couple of times we've had high TSS loads. So typically we're at 70, 80 milligrams per liter on our TSS, feeding the reactor. And we had some belt filter press issues, or times we needed to take it down for an extended period. And it's a learning process. So basically we had a lot of settling in those filtrate tanks just ahead of the anammox process. And we weren't, we hadn't seen this before. So we ended up sending a lot of solids straight to the reactor. And we had, sudden drops in DO and the ammonia removal process basically stalled momentarily until we can stop feeding the reactor and change the aeration mode, and we were back to loading it normally within 2 days. So and as was discussed in the design, it played out just like that. The high TSS load really mucked up the reactor. It was very, very visible. And within a day and a half, it cleared up pretty good with fresh filtrate. So again, it's all about the resiliency of this process. And so as the high TSS flushes out of the system, your anammox bacteria and your AOBs living on the media, they're staying in and they're ready to treat as soon as you start sending it. We also have filtrate heat exchanger installed in our filtrate building. That's a part of the design, and that's because we have cold winters here in Utah. I'm getting used to those, and the target temperature for the anammox process is 28 to 32 degrees. That's the sweet spot. But if you're within 25 to 35 C, you're still doing well. So we didn't quite have our filtrate heat exchanger operational or correctly installed in some places to give us the heat exchanger we needed to keep the temperature in that sweet spot. So we did see a drop in December last year, and we did lose a little bit of the ammonia removal, but I don't think we ever went below maybe 75% on our ammonia removal. So it stayed above design operation, even with the temperature dropping. So we did get that fixed, and we've had steady temperatures flowing to the reactor, and it makes a difference. With foaming can occur with a little excess polymer from dewatering or just a little over aeration. So we do have installed foam sprayers, and they use there's a submersible pump in the reactor effluent that takes the treated filtrate and sprays it back over the reactor. That's really effective at keeping the foam down. But we did notice in the winter that it can act as a heat exchanger, and if it runs too long on the cold days and nights, you lose your temperature in the reactor. So kind of limited use in the winter time. But we also have a water-based defoamer available, and that gets injected into the filtrate flowing into the reactor, and that's very fast acting. We've tried 2 products, and they're both really good, but they also kind of tank your DO if you add a little much. So we do watch for that. But foaming, it's mostly unsightly. It's not it hasn't affected the process much. We just don't like to see it, and if the wind picks up, it can maybe carry a little. But we have some pretty high free walls that or freeboard that keeps it in. Our biggest challenge came with the media rafting. So this is where the media began to float on top of the liquid and not mix well in the reactor. So, I mean, it's common. I've talked to other installations. It can happen in small amounts, but what we had in Rodrigo, if you can go to the next slide, was something the other places hadn't seen. So all that on top there, that's the media with the biofilm sitting on the reactor, and in places it's a couple, well, a foot and a half deep, I think at the most. So it was a big portion of our media, believe it or not, and in our ammonia removal was it was a struggle to keep it up. So what we had to do was to isolate 2 of the aeration headers in the reactor. And so you see there's 2 parallel lines of open reactor there where the media is not floating, and those 2 aeration headers stayed on. And that just helped with turbulence on top, and it kept the media rolling over at a good enough rate that it stayed. The biofilm did not die. It would get in the reactor enough that it stayed alive, and we were able to still treat and load the ammonia. Actually, we were above design load even while this was happening. So in the end, we ended up noticing that the gases, the nitrogen gas that's supposed to get released through the biofilm was getting trapped in there somehow. It may be that our biofilm was too thick, or it could have been a little excess polymer coming from dewatering, or I'm even thinking it might be one of the water-based deformers we use, that something was keeping the gas in the biofilm, causing it to float. So we use those, the foam suppression system with the sprayers. That's really good at keeping foam down. And it's also good at knocking the biofilm off the media if you need to, as we did here. And so we did that. We knocked the biofilm off. As you saw in the previous slide, it was quite a bit of weight loss for the media, but it got the media back in the process, and we're operating normally now. It only took about 4 or 5 days of constant spraying to get the majority of it back in, and yeah, we were back to loading. Actually, I don't think we ever went below design load. We're pretty aggressive here with our ammonia loading, so yeah, it's been a great process, and even here it was resilient and grew right back, and we haven't had any more issues with the rafting. So yeah, and I'll hand it back over to Regina for questions and answers.
All right, thank you so much. I had to find that mute button. Please, I would encourage each one of you, please, this is the opportunity to go ahead and chat to everyone if you have questions for our panel today. We do have one. What is the ammonia load in milligrams per liters? And you may have answered that already, but if not, if you would, please.
Oh, no, I don't think I did. So our ammonia loading in milligrams, we're designed to load above 1,000. That's what our filtrate is, but because of the BFP process, we have wash water involved and sometimes dilution water. So we're really at about over the year, it's been 560 milligrams per liter. That's what we're loading at. At times we did isolate the wash water from the filtrate, and we were about 900 to 1,000. And in those cases, you actually get you're more efficient on ammonia removal. So in the future, when our centrifuges and new BFPs are online, will be and the new BFPs will separate filtrate from wash water. We should see the higher concentration of about 1,000 milligrams per liter.
All right, perfect. And so we have another one here. How far above design load are you for the reactors?
So again, the current the interim design load is at about 1,100 pounds per day, and in the wintertime, to assist with the main process loading, we were taking on about 1,500 pounds per day. And, we were in conversations with Veolia the whole time to make sure, we weren't doing anything crazy. But, they just insisted that we, monitor closely all the parameters, and we certainly did. So we got up to about 1,500, maybe 1,600 for a little bit. But then with the media rafting, we had to come back down, and we've been about 1,200 pounds per day. And with the removal rates, we're about 1,000 pounds per day removed typically.
Okay, great. Are the basins open? Any effect during snow events?
I can answer that. So the basins are open. On the top, they're well insulated on the sides. So the main heat loss is from the top. I don't think the snow has really any effect. Snow itself doesn't. Really cold temperatures does have some effect, but snow going in there has no effect.
Okay, and Phil, this one may be for you as well. It says, howdy, Phil. Did you study the media to find out more about the media rafting? Has this happened only once?
So I'll also refer to Dustin on this, but we did look at it. And as Dustin mentioned, we couldn't figure out an exact cause of why this happened, other than we thought that nitrogen gas may be trapped in the biomass. And I believe it has happened only once. Dustin, you have anything to add there?
It has only been the once, and as far as studying, we Veolia had the idea to test whether the media, as it was rafting, whether it was floating differently in the reactor liquid versus untreated filtrate, to see if we noticed any change there. And that's when I did that test, we noticed just media with more biomass was rising and not really floating in the liquid versus I tested unseeded media and media with just less biomass. And so then, you poke holes in the biomass around the media and then drop it back in, and all of a sudden it's, not rising. That kind of gave us the hint, oh, it's, something's probably trapped in there. So that's when we began spraying off the biomass, and yeah, it's grown back well, and we haven't had any issues with rafting since.
And I'll say for Veolia, for the question of covering the tanks, most of our anammox reactors are not covered, whether it's in a cold or warm climate. And then in terms of rafting, it's not a common occurrence. So this was new to us as well.
All right, perfect. What is the maximum TSS concentration to anammox? Any pre-treatment required?
Yes. So on this, we do pre-treat. So our filtrate can have up to, say, 500 to 1,000 milligrams per liter of TSS in it. And we put that into our filtrate equalization tanks and settle the solids and pull those off the bottom. Those are returned to the headworks. And then the filtrate on top is what's going to the reactors. I think we're in the 40 to 70 milligrams per liter generally of what's going into the reactors. But as Dustin mentioned, we had an event where we had like 20,000 milligrams per liter of solids going into the reactor. And that did cause a problem until it could wash through.
Okay.
Right. So for Veolia, you don't necessarily need TSS pre-treatment, although having a 20,000 level event is of concern. But as long as it's not continuous, it should flush through, like Phil mentioned.
Okay, great. We've just got just a few more moments. We'll try to kind of push through the rest of these. If we're not able to get to your question today, the panelists will receive your question and may be able to reach out to you to respond. What is your effluent ammonia concentration? Do you have to add alkalinity to be able to maximize removal?
In the reactor, we have very alkaline waters here in Utah. Kind of in general, we don't have to add any alkalinity in our main plant or to the reactor. Our effluent ammonia from the reactor generally is, say, like about 40, 50 milligrams per liter or so.
And let's see, do you want to, we'll go ahead and just push through, see if we can get these last two questions answered. Can you talk about the configuration for solids removal in the EQ tank? How often do you remove solids from the EQ tank?
Dustin, you want to address this one?
Absolutely. So the EQ tank is a cone bottom, and the feed pump to take filtrate from the tank to the reactor, it's above that, and the solids pump, the filtrate solids pump, suction pipe goes down to the center of that cone. So the filtrate comes in the center, and it settles as Phil described, a clarifier, and the solids settle. And so we're only pumping once a week. We do 10,000 gallons once a week out of the bottom of that tank, and we're slowly, cutting back. We're just testing to see what's best for us. So right now we're about 10,000 gallons a week, and we send that back to Headworks.
Okay, perfect. And we'll make this one our last one. Again, if we were not able to get to your question, we will be sending these questions over to our panel so that they can respond to you via email. How are tanks insulated, above ground or below ground?
I'll answer that one. So the tanks are reinforced concrete, and outside of the concrete below ground, there's 4 inches of rigid foam insulation, and then the earth. Above ground, the tanks have a brick veneer on them, and between the concrete of the tank wall and the brick, there's 4 inches of rigid foam insulation.
All right, great. Well, this has been great. We've got some very positive feedback that's in the chat, thanking everyone for a great presentation today. Gentlemen, if you'd like to say any last words to our attendees, definitely want to thank Veolia for sponsoring today's webinar. And I will hand it over to you if you want to say some last things. Otherwise, I will close us out in just a moment.
Yep. Thank you all for joining the webinar. And thank you, Phil and Dustin, very much for letting us know how your experience has been with the anammox side stream treatment.
Yeah, I'd like to thank all the attendees. Looking at the chat, I know a lot of people on the list here, so I appreciate everyone signing up for this and attending and seeing what we're doing. So thank you.
Yeah, thanks for the opportunity to present, and thanks for Veolia, all their support and startup and operation.
All right, perfect. Well, this actually concludes today's e-showcase. Thank you all for attending. The recording will be available at buyersguide.wef.org. We will send all registrants an email tomorrow with that link, and a certificate of participation will be sent to you as well. Please visit our event calendar to sign up for future webcasts. And thank you very much, everyone.
Thank you.
Thank you.